This is Statistics 243 for Wednesday, November 19th at UC Berkeley. Okay, so we're going to continue our discussion of various methods for multivariate optimization, and we'll see some examples. So we talked last time about a few different ways that were basically related to Newton's method, and we'll see some other variations on Newton and Newton-like methods today. And then we'll also talk about some other approaches that don't really involve gradients in the same way that Newton-type methods use. Okay, so far I want to sort of generalize here from what we've seen already, which is that usually when we've been talking about Newton's method, we've seen something that looked like this, except we had the Hessian here instead of alpha times m, but we had it was basically of this form. And so the idea is that a Newton-like method is going to have the same basic form, that that we're going to have some matrix that might be an approximation to the Hessian, but maybe is not exactly the Hessian. And then we're going to have this alpha, which is just going to be a scalar, and that's going to allow us to scale the distance by which we walk in that direction. But we're still going to make use of the gradient, and so it's going to in some ways look sort of similar to what we've already been doing. So basically, the gradient's going to tell us something about, roughly speaking, what direction do we go so that we're going downhill to do the minimization. This matrix M is going to allow us to accommodate. Is basically going to allow us to sort of adjust that direction, and the alpha is going to basically allow us to adjust how far we walk in a given direction. Okay. So that's the sort of standard template that we're going to think about here. Okay, so let's actually step back from that even a little bit and make it a little bit simpler, which is, suppose that I could think of any of these steps in an optimization as basically, what do I need to do? I have some place where I currently am. That might be my starting value, or it might be I'm partway through the iterations. And where am I going to go in terms of trying to go down to the minimum? I'm going to try and choose a direction in a smart fashion. And once I choose my direction, I need to figure out how far am I going to go in that direction before I stop, and then I'm going to repeat the process. I'm going to sort of try and figure out a good direction to go, and I'm going to move a certain distance in that direction. So that's the basic paradigm that we're thinking about here. And once we've chosen a direction, we can now think of that as basically univariate optimization. We're walking along a line a certain distance. And so I could do some of the techniques that we've already talked about a couple days ago for doing univariate optimization, but in this context after I've chosen the direction. So all of those kinds of ideas could come into play. Okay, so if we're thinking about this and we think about what direction to go, the sort of easiest thing to think about is, why don't I just make use of the gradient directly, right? The gradient is going to tell me what the direction of steepest ascent is, and so when I do minus the gradient, it's going to tell me what's the direction of steepest descent from where I am. So that seems like kind of a smart thing to do. I'm here, I look around, I can travel downhill most directly if I go in this direction, most steeply if I go in that direction, so why don't I just start walking in that, why don't I just start moving in that direction, okay? So that would be sort of the basic intuition of let's just walk downhill, and that should get us in the right place, eventually get us to the right place. And I could, in fact, once I estimate the gradient and start walking that way, I could find the precise minimum in that direction by doing a single directional search. Okay, so any questions about that sort of setting of the stage here, of what the problem we're trying to solve here? Okay. So one question is, well, why do we have all that business with using the inverse of the Hessian or this M matrix in place of the Hessian? Why are we bothering with all of that? That just seems to make things more complicated. We have to deal with second derivatives. We have to deal with inverses. Why would we ever want to do that? And the basic reasoning is that if you do just walk downhill in the direction of steepest descent, you'll tend to zigzag. So this is a basic illustration of what will happen. I don't know how easy it's going to be to see the contours of this in the back, but if I were to start here, and obviously if I'm sort of omniscient, and especially in 2 dimensions, I can just plot this, so it's pretty easy to see where I need to go. But as soon as I get to higher dimensions, I can't just look at this and determine in what direction they need to travel. All I can do is think about evaluating gradients and second derivative matrices from where I am and trying to use that kind of information. So I'm here, and if I look at what these contours look like, they basically look like this at this point. And so the steepest direction downhill from this point is to go straight up. Okay? And if I start walking straight up, and in this case I wrote the code so I actually find the exact minimum in this direction. So to find the exact minimum in this direction, I get to there. Now I'm starting to look at what the steepest direction downhill is, and it turns out that it's to go this direction. So again, I minimize. But you'll notice what's happening here. I start walking downhill here, and I'm sort of not really quite doing what I want to do. What I really want to do is walk that way. But because of the exact gradient value here, I don't sort of travel down this valley. I sort of travel along the side of the hill because of what the local information that I had at this point. So this is very typical of if you use steepest descent. You'll go downhill, but you'll tend to zigzag in the process of doing that. I've sort of illustrated that here in another example where that's actually a quadratic function, so it's actually just, those are elliptical contours. Here's another example where it's not quite elliptical. If I were to start here, the steepest direction downhill is here, and so I'm not actually moving towards the point that's presumably the minimum over here. I'm moving sort of towards that point, but I'm not moving as efficiently as I might. Okay? And you might think about, well, how does that contrast with if I actually had circular contours? This is going to be much better, because basically whichever point I start at, directly downhill, if these are truly exact circles, directly downhill is just going to be straight towards the center here. Okay. So anything you can do to get to a case where you basically have circular contours in 2 or more dimensions as opposed to these elliptical or other shaped contours is always going to be a good thing to do, because then you could just travel downhill basically. So there are a couple of different ways of interpreting what Newton's method is doing. One of them is that when you apply that h inverse function, or more generally apply some n inverse function, is you're basically taking this picture and you're basically doing a transformation that sort of shrinks this direction to make it more elliptical, and then more circular contours, and then you're able to travel more efficiently by doing that sort of transformation. The other thing that you can think of as Newton's method is doing, or taking account of second derivatives in some fashion is doing, is I have this local information on the gradient here, but when I calculate the second derivative tells me something about the change in the gradient, right? It's the derivative of the derivative. And so if I knew, for example, that, yeah, the gradient at this point is going in this direction, but that the change in the derivative is such that basically sort of the change in the derivative is sort of that the derivative is starting to look more like this, to go downhill in this direction. So another way of thinking about Newton's method is that you're basically modifying the gradient to account for the information you have about what the change in the gradient is at that point, or the derivative of the derivative is. So either way, that's sort of trying to motivate why it's useful to use the second derivative information and not just rely on going most steeply downhill. Any comments or questions? So I guess I won't bother to run this code. This is just to show you that, just so that you could have the code here that illustrates this concept in the picture here. But you'll notice if you look at this code here, what I'm doing is I have my function, and then I have the gradient function, which is what I'm calling f prime or fp here. And this is just a quadratic function here. It's a function of x1 and x2 and x1 times x2. And so the thing that I've encoded here is I've basically said, okay, I'm going to choose my direction based on evaluating the gradient function. And then I'm going to optimize over alpha, which is the amount that I'm going to move in that direction. And in this case, I'm actually doing an exact optimization. I'm going to use the optimize function, which does a one-dimensional optimization, and it's actually going to find the exact optimum in that direction numerically. Part of the reason that I'm drawing this idea out here is if we're in the middle of doing iterative steps where we walk a certain amount in a certain direction and then we turn and we walk a certain amount and then we turn again and we walk a certain amount, you don't have to walk all the way to the precise minimum in the current direction you're going, because you know you're just going to have to take another step in some other direction. So there's not much point in using a whole ton of computation to find exactly how far to go in this direction. I just need to make sure that I walk downhill a reasonable amount in that direction, and then I could stop and go find my next direction. I don't have to find the exact minimum in that direction. So in this code, I am finding the exact minimum in each of the directions, but that's not something that in general would be good practice from a computational efficiency perspective. Okay. I guess I've sort of said most of this business here. The other thing to point out is that if I weren't doing exact optimization, say, in any one of these directions, I could just go a certain distance and make sure that I've gone downhill from here. And I could also, suppose that I take suppose I have some step size that I just have come up with from out of thin air or whatever. And suppose my step size says, oh, walk this far. I could evaluate how big the function is here and how big the function is here and realize maybe this is actually higher than it is here. I know the gradient is pointing downhill, so I know if I go backwards, I'll get to a point where I'm going downhill, even though, what has happened here is that I've gone too far. So I've already sort of discussed this idea of backtracking, but it comes up here as well. You know, if I have a step size that takes me too far, a reasonable thing to do at this point would be to backtrack, say, halfway backwards, and make sure that that's gone downhill, and then I'll use the backtracking and the halfway backwards. Maybe I end up here, and now I can choose my new direction and go in this direction. So a lot of these ideas get combined together. Okay. So let me say a little bit about something called these quasi-Newton methods. So again, the basic idea is we're replacing the Hessian with some other function, some other matrix that tries to approximate the second derivative information. And so part of the reason for doing that is suppose that we're searching in a p-dimensional space, and p is 1,000 or 3,000 or something like that. So we're solving a high-dimensional optimization. If I have to calculate a whole matrix of second derivatives, that's probably going to involve a lot of computation to calculate that entire matrix. So I probably wouldn't want to recalculate that matrix every single iteration. That would involve a lot of calculations. So the idea of a quasi-Newton method is that you want to come up with an M matrix in a more efficient way. And one way that you might do that is if I'm here and I have some M matrix and then I move here, the M matrix that I would calculate here, the matrix of second derivatives that I would calculate here, is probably somewhat similar to the matrix of second derivatives here. So maybe I can make use of this matrix, modify it a little bit, and get an approximation of that matrix here without recalculating the entire matrix of second derivatives. So that's sort of the basic idea behind this idea of doing quasi-Newton method. And in particular, one of the standard methods that gets used is something called BFGS, which is a Newton-like method, and it's one of the standard methods used in the optim function in R. So BFGS uses this kind of idea. Okay, so one way to think about what BFGS is doing is, again, I'll go back to my picture here. Suppose I had an estimate of the second derivative matrix here, and I had an estimate of that second derivative matrix here. By virtue of having gone from here to here, I actually have a numerical estimate of basically of what the derivative is in this direction. Okay, so so suppose let me backtrack a little bit there. Suppose if I've estimated the gradient I'm estimating the gradients at all of these points here, right? So if I've estimated the gradient at this point, and I've estimated the gradient at this point, and I know how far I traveled, the difference in gradients divided by the difference in the x values is actually a numerical estimate of the second derivative, because it's the derivative of the gradient. So as I sort of move along here, I'm sort of accumulating information in the process of doing some of these calculations of calculating the gradients. So the idea of, one of the basic ideas of these Newton-like methods is to try and update this M matrix with the information that you get as you move along. And so there's something called the secant condition, which says that if I've calculated the gradients for xt plus 1 and the gradient at xt, if I can satisfy this equation, this is a matrix, this is a vector, this is a vector. So I can't really take this vector and divide it by this vector and get a matrix. That doesn't really make sense. It's not the right dimensionality. But if I just sort of roughly think about doing that in a very vague sense, what do I have? I have mt plus 1 is equal to the gradient of f at xt plus 1 minus the gradient of f at xt divided by xt plus 1 minus xt. Well, what's this? This is just a numerical approximation to the, this is basically a numerical first difference estimate of the gradient of the gradient. So that is basically an estimate in one direction of what the second derivatives are. So that's sort of a loose interpretation of what this secant, what this equality means. And so the idea is basically to update my mt to a new mt plus 1 in a way that satisfies this, which means we're sort of taking account of the information we've learned from having traveled, from having done one of these steps, that we've learned something about the change in the gradient over that relative to that change. So that's basically what well, let me step back a second. So one way to write out an update to mt that satisfies this condition is it looks like this. And if we see what yt and st are, yt is just the change in the gradient, and st is just the change in the x's, and those are the pieces in here. If you look at this, you should be able to see that this is a rank 1 update to mt. So we're taking our mt and making a rank 1 update to get to mt plus 1. So why is this a rank 1 update? So this piece here, what is this, a matrix or a vector here? Y minus mt st. It's a vector. Right? So this is an outer product of a vector with itself to create a matrix. So that can, of course, only be rank 1 because we're basically creating a matrix out of a single vector. So we can't get it to be any more than a rank 1 thing. It's just a linear combination of the original vector, basically. So this is a rank 1 update to mt. It's basically adding some information about the second derivatives that we've learned from doing the calculations of the gradients at these 2 points. So BFGS is almost like this. BFGS is actually a rank 2 update that people have worked out as being a reasonable update that in general will preserve positive definiteness of this matrix when we modify this matrix to get to that one. And remember, we're doing the inverse of it when we do the update, so it's good to have it be positive definite. So I won't sort of delve into any more of the details, but you can see what it stands for. These are the 4 people who discovered or came up with this method. I never knew it was so funny. Okay. So that's basically what happens if you run Optim in R and use BFGS, is you're basically doing Newton's method, but you're doing Newton's method where you don't recalculate the entire Hessian matrix every time. You do some updates like this where you're basically trying to do some cheap approximations to the Hessian matrix. And it probably also has some checking in it to make sure that you're not stepping too far in a given direction and they don't start going uphill and things like that when you do the unidirectional updates after you've decided on the particular direction to travel. Okay. The other comment I wanted to make is even though we're approximating these Hessian second derivative matrices as we go along, if we're maximizing a likelihood, at the end of the day we're going to get to the maximum likelihood estimate. And if we want to get an asymptotic covariance, and the asymptotic estimator of the covariance matrix for the maximum likelihood estimators, what we need to do is we know that by a standard asymptotic theory that the maximum likelihood estimator is approximately normally distributed, centered on the true values of theta, and then that an estimate of the covariance matrix for the MLE is minus the Hessian evaluated at the MLE, and then taking the inverse. So at this point, you wouldn't want to use an approximation of this Hessian matrix. You'd want to actually go in and numerically get a good estimate of this Hessian matrix to do in order to come up with standard errors for your estimator. So this relates to one of the problems on the problem set. But just to comment on, even though we're doing these approximations as we find the optimum, at the end of the day, when we get to the end, we do want to get a good numerical estimate of this matrix of second derivatives. Okay. Questions, comments? I guess I'll also comment as we're thinking about optimizing as we're thinking about shapes of surfaces and about some of these connections between sort of the numerical procedure and the statistical interpretation. If I did the negative log likelihood and I'm doing minimization, then this becomes a plus. So you just take the Hessian of doing the minimization. And the other thing to think about is once I get down and I find the minimum, suppose the contours look like this. What I'm basically doing by taking the Hessian is I'm basically making a quadratic approximation to the likelihood surface evaluated at the maximum likelihood estimate. So I'm basically saying, okay, here I am. The asymptotic covariance is basically to take whatever the surface looks like, fit a quadratic approximation to it, which is what is going on with the Hessian. And the curvature of that quadratic approximation tells me something about the uncertainty in my parameter estimates. So if I had a surface, I've sort of already said this in a slightly different context, if I had a surface that looks like this, and I think about a quadratic approximation at the minimum, I have a lot of certainty about this direction in the parameter space, and I have less certainty about this direction in the parameter space because the likelihood surface is flatter in this direction and steeper in this direction. So the statistical interpretation of what it means to be doing this goes hand in hand with sort of thinking geometrically about this surface and thinking about the optimization that we're doing as we move through this space. Okay, so I guess that's basically all I'm going to say about Newton-like methods. I want to introduce a couple other methods, one of which gets used a lot in certain kinds of statistical model fitting, and that's called Gauss-Seidel. And then the next thing I'll talk about is something called Nelder-Mead, which is basically a non-Newton method that is one of the other standard things that gets used in Optim in R for doing optimization, and that doesn't rely on using gradients. Okay, so Gauss-Seidel, some of you may have heard the term backfitting if you've heard about generalized additive models. And it's also called cyclic, I guess, coordinate descent. So the basic idea of Gauss-Seidel is really not any different than some of the things we've already talked about, which is Gauss-Seidel basically, it chooses the directions of travel in a very simple way. It just says go in the axis-oriented direction. So if I were trying to optimize with respect to x1, x2, x3, x4, x5, etc., I'll just choose to optimize in the x1 direction and do a univariate optimization. Then I'll choose to optimize in the x2 direction and do a univariate optimization. Then I'll choose to optimize in the x3 and do a univariate optimization, and then an x4, but I'm running out of dimensions that I can work in. But it's very simple. So one of the appeals of doing Gauss-Seidel is that you don't have to think very hard about what direction do I travel in and how do I calculate all these gradients and derivatives. I just choose the axis-oriented directions, and I'll do a univariate optimization, and I'll just do a whole bunch of univariate optimizations. So conceptually, it's quite simple. This gets used in a couple places if you look particularly in the older literature on fitting generalized additive models. So this would be if you're fitting a regression model, and instead of having the expected value of y be x times beta, which is beta 0 plus beta 1 times x1 plus beta 2 times x2 plus beta 3 times x3, etc., so just a linear function. Here we have an additive function of potentially nonlinear functions of each of the covariates, but each covariate only enters into one of these functions. And so a standard way, particularly historically, of fitting these kinds of models has been, suppose I have an estimate for all of the other f's, and now I'm going to try and estimate what a smooth function of z1 is that relates to the observations. So I'll estimate this function holding the others fixed, then I'll move on and I'll estimate this function holding the others fixed, and continue on in that fashion. So that basic idea of sort of cycling through things and holding everything else fixed is sort of the basic idea of doing backfitting. Okay, so you shouldn't be surprised to learn that if when we're looking at steepest descent, we saw that it could zigzag. If we use Gauss-Seidel, it's almost certainly going to zigzag because we're not choosing the directions even to go most steeply downhill. We're just arbitrarily saying I'm going to move in the axis-oriented directions. So I'm going to take that same example of that quadratic function, and now what I'm going to do is I'm going to go the axis-oriented directions, and I'm going to do a univariate full optimization in each of those directions. Again, you don't have to do the full optimization. You could just go downhill a certain distance and not do the full optimization in the single direction. But here's Gauss-Seidel for that same problem. And I think it might actually be the same starting value as I used before, and if not, it looks like it's fairly close. Well, so what do? In 2 dimensions, it's obviously clear that I need to go in this direction, right? But if I decide to move in the x1 direction at first, my only choice is to go this way or to go this way. And at this point, it's downhill to go this way, so I start moving in that way. So in some ways, it sort of looks like I'm going the wrong direction, even though it is actually going downhill, right? So once I do that, now the next step is to move in the x2 direction, so I move downhill to the minimum in that direction. Now I just keep going, and then I'm going to zigzag all the way down to the minimum. So it could take me a while to get there, as opposed if I did Newton's method on this, what would probably happen is I would probably do a step like this, and then maybe a step like this, and a step like that, and I'd probably get there in 4 or 5 steps. But instead, I'm doing it with all of these little piecewise steps to get to the minimum. Okay. But that being said, in some problems, this is sort of state of the art, and is a standard thing to do. Those of you who may be familiar with the lasso, so this is basically a penalized regression model where this is just a regression model where I take the sum of squares. So this is the usual objective function that I'm trying to minimize when I do ordinary least squares. But this puts a penalty on the absolute value of the coefficients of the beta values. So that is the lasso. And if you look at, I don't think I'll bother to go through the details here of sort of writing out what the derivatives are and thinking about this too carefully. But if you look at the GLMNet package in R, which implements the lasso and is sort of standard software for doing this, and if you look at the paper that was written to describe the GLMNet package, they basically describe a whole bunch of these, a few different coordinate descent methods for fitting this lasso problem and finding these coefficients, the betas. And those are all coordinate descent methods. Some of them are smarter than others in terms of making use of sparse matrix kinds of calculations, but they're all basically choosing, they're basically saying, okay, I'm going to go in one direction, then I'm going in the next direction, then the next direction, et cetera, et cetera. Okay. Okay, so any questions about that? Okay, so the next one I want to describe is something called Nelder-Mead. I think this actually might be the default for Optim in R. And one of the nice features of Nelder-Mead is we're not going to rely on making use of derivative information at all. So we don't have to do all the calculations to do the derivatives. We don't need to either calculate numerical derivatives, or we don't need to derive derivatives and pass them into the optimization routine. And it could presumably work for surfaces that are not differentiable, but say but are just continuous and not differentiable. So when you look at it, it sort of looks a little bit complicated, and there are a whole bunch of different steps. So I just want to sort of walk through a little bit of the intuition of what it's doing. Okay, so the idea is you're going to take let's think about the dimension of the space we're optimizing in. So it's a p-dimensional space. So if we have a p-dimensional space, we're going to take p plus 1 points in that space. And those are basically going to be our starting values. And at every step, we're going to replace one of the points in that set of p plus 1 points with another point. And so the idea is we've got the set of points, and the idea is to sort of move it's called a polygon when you have this many points, a polytope, I guess, is to basically walk that polytope around the space in a smart way until you basically find the minimum and until you basically get in the location of the minimum and sort of zoom in on the minimum. So the question is sort of how you go about doing that. Okay, so as usual, it's hard to think in high-dimensional spaces, so we're just going to think about doing this in 2 dimensions. So in a p equals 2-dimensional space, I'm going to have 3 points, and they're going to make up a triangle in this space. So I'm going to come up with some starting values that form a triangle here. And I'm going to evaluate my function at each of these 3 points. And I'm going to order the values of, I'm going to sort of label my x's as x1, x2, and x3 based on which ones are the smaller ones. So let's say this ends up being f of x1, or so this ends up being x1, and I'm going to have calculated f of x1, and this ends up being x2, and I'm going to have calculated f of x2, and this ends up being x3, and I'll calculate f of x3. So x1, x2, x3, I don't know the labels until I calculate the function in each of these, and then I decide that this is less than this, and that's less than that. Okay, so now let's sort of try and develop some intuition of how we would move around in this space in a smart sort of way. So suppose that I told you that this value was a lot bigger than either of these 2 values, and I'm trying to do minimization. What would I want to do to sort of adjust my triangle and replace this point to try and move towards the minimum, if that's all that I told you was that this value is a lot larger than the other 2? Okay, so move it to
the other side of x1, x2.
Okay, so the idea is if this is bad and these are better, I sort of want to go in this direction somehow, right? So I want to modify my set of points in some way that I want to move this point sort of closer to these, or maybe I want to move this point and jump all the way over and go over here, because if this is higher than these 2 points, and say these 2 are about the same, that might mean that the whole surface is downhill in this direction. I want to go really far in that direction. What if instead there was one point, let's actually make it this one. Suppose this point is a lot lower than these 2 points, then what do I want to do? Nick?
Let's go to the direction to fx1.
Right, so I just want to sort of move in that direction, and maybe I might just want to sort of contract these 2 points towards that if it looks like this is a lot better than those. So again, we're not sort of sure whether we need to overshoot or whether this is pretty good and we just need to move towards there. But those sort of those sort of 2 things that we just drew out as some intuition of what to do is basically what Nelder-Mead does, except in arbitrarily high dimensions. So there are going to be a few different kinds of moves. So in a lot of these kinds of algorithms where we're doing optimization, you get there's going to be this idea of sort of making moves and having different kinds of moves to deal with different kinds of situations, and that sort of happens here. So there are going to be 4 different tuning factors. There's a reflection factor, an expansion factor, a contraction factor, and a shrinkage factor. So anytime you see a Greek letter, just think of that as some tuning parameter that we could sort of choose that will determine, as we sort of see what these values of f are, if we sort of move over here or we shrink towards that, how much do we shrink or how much do we move, and those sorts of manipulations. Okay, so this is in words what happens, and I'll sort of try and refer back to this, but I think maybe the best thing to do is just to see an example in the actual R code. Okay, so that was the Gauss-Seidel stuff. Okay, so I've just chosen some of these 4 different tuning factors. I think I might have gotten this from how Optim implements it, but I don't remember. And I have a little function plot_seg that will plot line segments for me, because we're going to be plotting a bunch of these sort of triangles and whatnot. Okay, so I'm going to come up with my, actually, what's my f function here? Oh, actually, I don't even have an f function here. I'm just sort of plotting out what might happen. Okay, so the idea is suppose these are my 3 points, and now suppose that this is the worst point, and I think I just decided that this was the best point and this is the second best point. So it's this idea that we probably want to go sort of in that direction. So the idea is I'm going to choose x bar to be the mean of the remaining points of the better points. So okay, so there's xp plus 1. Sorry, that didn't really come out very well in terms of labeling. And there's the mean of the better points. So this is the worst point. Here's the mean of the better points. The idea of the first move, which is the reflection move, is I'm going to move along this direction, along the line that connects these 2 points. And so the first thing to try is to basically do a reflection across here and move out to here. And one of those scaling factors determines if I do this reflection, basically I reflect across here, I move over here. How far over here do I move? That's one of those tuning parameters. So if I do, so I guess that's that alpha value. So this is just setting up the reflection move. So this is a candidate point that I might want to add. I might want to replace this point with this point if I do this reflection move. So what the algorithm says is, okay, so this is our proposed new polytope, our new triangle in this case. And the idea is, well, should I use that new red triangle, or have I gone too far? Okay, so basically what you're going to do is evaluate this point, the value of the function at this point relative to the points you've already calculated. And if this point is actually the best of all the points, what does that tell us? It tells us we really do want to be going in that direction because this is lower than anything else. So at that point, there's an expansion step which would actually move that even further out here and walk the triangle in that direction. On the other hand, now I have to sort of go back to the notes to remind myself exactly how this works. Okay, so I just talked about the reflection. Okay, so if that x sub r is between the best and worst of the other points, then we're just going to use that red triangle. So, so if this is the best, we want to go further. If it's, as long as it's not the worst and not the best, then we basically want to replace the original triangle with this new triangle. And if this is still, if this was originally the worst point, if this is no better than these 2 points, then we have to see, is this any better than this xp plus 1 point? And then decide how to move based on that. So let's see. Right, so the expansion. Okay, so if f of xr, if f of the proposed point is worse than all the other points, oh, okay, but better than the original xp plus 1, then we're going to use that xr. And if it's worse, then we're going to let x. Oh, I see. Okay. So so basically, depending on which of these is better, we're going to choose this as sort of an interim point, either this one or this one. And then there's going to be a new sort of sub-step at this point, which involves potentially some contraction. So that's this xh. Xh is either going to be the xr point that was the reflection point, or the original xp plus 1. And now what we're going to do is basically we're going to do a contraction where is this here? Okay, so that was the potential expansion if it seemed like going in that direction was really good, and that would be the new triangle if we did expand. And if the expansion didn't look good, then we might be in the situation of going back to HP plus 1 and doing a contraction, and that contraction would look something like this. So if it turned out that this was not better than this, then we've sort of explored this part of the space over here. Nothing's looked particularly good over there. So at that point, the best thing to do might just be to sort of contract towards this point here, since I know these two are better than this one. So contract and make this blue triangle here as my next step. And that would be in the case that. Sorry, let me go back to. I'm sort of getting slightly confused about these last 2 points. So if. Oh, okay. So the contraction, we'll accept that contraction if the result improves upon f of x plus h. Okay. So this is the proposed contraction. And if this is better than this, then we'll accept this contraction. We'll have our new blue triangle. But if this actually isn't any better, if this is worse than this, then the idea is actually let's just move towards the best of the three values. So suppose this is the best of the three values. We've sort of not done, none of these things that we've tried going in this direction has helped. And so at that point, the idea is let's sort of shrink everything towards the best point and move in this direction. So at that point, that's the shrinkage step. And so the shrinkage step would look like this. Is we're going to take each of these 2 points and move them both a certain fraction. In this case, I think it was just half towards the best point, and this is going to form our new triangle. Okay, so that's sort of the basic strategy of sort of what you would do as one step. As a result of having done that one step, you'll either get this new triangle, or this new triangle, or this new triangle, or this new triangle. And that's your next iteration, and now you start from that triangle and do the same thing all over again of sort of figuring out how do these points all relate to each other, and how do we move, and which of these kinds of steps do we do. And so eventually the idea is that you sort of walk this triangle towards, as I said before, you sort of walk the triangle towards the minimum, and the triangle should contract around the minimum as you get close to the minimum. Yeah?
So this algorithm still tries to find the local minimum instead of global, and still rely on the starting value, right?
Yeah, so there's still going to be sensitivity to the starting value. I think that there's probably going to be less sensitivity because we're not relying on gradients. But it is sort of going to depend on exactly what the surface looks like and how you start your points as to where it goes. I mean, you could imagine, I'm thinking on my feet here, I haven't really thought about this too carefully, but if we go back to our original black triangle here, you can imagine if there's some local minimum over here, but then there's a global minimum over here, depending on what these values are, you might sort of move in this direction, but you also might still move in that direction, depending on sort of the relative magnitudes of the local minimum and the global minimum, and the exact values of the function at the points that you have. So you might actually, I don't think it's necessarily going to go to the local minimum, but it might, depending on sort of how you start and what the values end up evaluating to. But that's a really good question, and one that one should always have in mind when one is thinking about different optimization methods, is how is it going to handle whether the case that you might have local minima and not just a single global minimum. Other questions or comments? Okay, so I think maybe I'll close by just saying a few things about something called simulated annealing, which sort of goes hand in hand with this idea of local versus global minima. And then for next time, we'll start in next time by talking about the optimum function in R and how you use it to do some of these methods that we just talked about. So the idea of simulated annealing, and I don't want to go into a ton of detail, I just want to give you guys a little bit of intuition about handling cases where you have local minima, is there are sort of 2 key things to doing simulated annealing. One of them is, if you think about your objective function, you're going to start by sort of flattening it out. Because what's the danger when you're doing something like a Newton-like method? Suppose you've got something like a function that looks like this, right? And you're trying to find this point here. But suppose, if in multiple dimensions you can't see this, right? All you can do is evaluate the function and see how big it is. And suppose you start here and you do some Newton steps. Well, you're just going to converge down to here. You're never going to have any chance of getting over here. You could try starting a lot of different starting values, and maybe you get lucky enough with one of the starting values that you'd be in the domain of attraction of this particular minimum, and you'd actually find it, and you know that's better than this one that you would converge to from another starting point. But you're likely to fail in this sort of situation. So one of the key features of simulated annealing is basically that you're going to it's sort of going to be an iterative procedure. It is an iterative procedure. You're going to modify this function in such a way that you basically sort of shrink the variations in the function. So you're going to sort of flatten out the function. You're going to make sort of a flatter version of this function. It's still going to have the same places where there are the dips, and they're still going to be sort of relative to each other. You're still going to have the global minimum in the same place. But you're sort of going to flatten it out so you sort of pull this up, and you're going to pull the peaks down so it gets flatter. And in fact, at this first step of this, you'd want something that was pretty flat, like this. And the other part of simulated annealing, like Markov chain Monte Carlo, if any of you have encountered Markov chain Monte Carlo, is it basically proposes to move. It proposes a new value. It proposes to move in a certain direction. And in a lot of what we've been talking about, we've only been going downhill. Right? We've gone from one place, we've tried to make sure that every step goes downhill. If you're dealing with this sort of local optimum problem, in some cases you might actually want to be able to go uphill for a little bit, because going uphill will allow you to get over some of these local humps and hopefully sink down into the global minimum. So the basic idea of simulated annealing, and we're not going to go into the sort of algorithm in much detail, is you flatten out the function and first work with a problem that looks like this. And you set up a problem where you're basically proposing moves such that if you propose to go downhill, you always go downhill. But if you propose to go uphill, you have some chance of still going uphill, particularly if you don't propose to go uphill very far. So the idea is that you're going to be moving around in this space here. If you start out here, you might be able to get over this local hump and into the next trough over. It might also happen that you might be in this trough and you might move away from the place where you ideally would want to be. But the idea is that you can sort of move over this space, and then as you go through the iterations, you basically transform the flattened version of the problem into a slightly less flattened version of the problem, and eventually into the actual problem that you want to solve. And if you sort of can carefully control how many steps you make and exactly how you decide whether to accept to go uphill or not, the idea is that as you transform from this problem to this problem to this problem, that you're fairly likely to sort of end up in the global minimum, and basically you get trapped in this trough as this gets deeper and deeper as you go from here to here. So that's sort of the wordy explanation of what simulated annealing does. It's not guaranteed. You could certainly, as you go through this process, you could certainly get trapped in this local minimum and not get trapped in the global one. But the idea is if you do this slowly enough, and if you sort of tune things appropriately, then the hope is that you'll get trapped in the global one. So this says a little bit more in detail about what the algorithm looks like, but not in a huge amount of detail. And simulated annealing is implemented in the optim function R, although I don't think I'm going to talk about it in any more detail. So if you're looking into simulated annealing and you read about it, you'll hear about the cooling schedule, and the cooling schedule is basically how fast do I transition from this very flattened version of the objective function to the actual objective function. How fast do I transition from this to this to this, et cetera, et cetera. Okay. It can still be helpful to have multiple starting values, like in any of these kinds of problems. All right. Any questions or comments? Yeah, Eugene.
So in implementation in R, is the proposal of moves still uniform across the entire X direction?
I'm not sure. Do I have any comments here of when I looked into this? I mean, it's based on a Markov chain Monte Carlo. So basically, if I were here at this point, I'm going to propose to move, and usually Markov chain Monte Carlo methods propose to move locally from here. So it's not going to be often. It's not going to be proposing uniformly. It's going to say I'm going to move a certain amount away from this place.
There's some delta, but it's uniform across that delta. It doesn't actually. So I know that some of the novel the methods, they try to adjust how far you move the delta, basically, proportional to the cooling schedule. So the higher the temperature, for example, the more it wants to jump, and then as the T goes down, the moves become more localized.
Okay. Yeah, I don't know too much about it. I don't know exactly what R does, but you can imagine as I've sort of described this, there's sort of how do I choose how to move, how fast do I choose how to do this. There's a whole bunch of tuning and sort of expert opinion that goes into doing this. And that sort of at least vaguely relates to what Eugene was asking about. Okay, so let's stop there, and we'll pick up with section 6 on Friday. So basically, the first part of Friday we'll talk about using optim in practice, and I think what I'll do in the second part of Friday is talk about the EM algorithm, and both of those are going to be useful for the problem set problems.